Hi viewers, this is Sriramulu, degree lecturer in physics, a YouTube channel, S.S Space Physics. So, today's topic is a maximum power transfer theorem, right? Maximum power transfer theorem. So, that theorem can explain to us maximum power will be delivered. When, at what condition it delivers, that is we have to know in this theorem. So, statement: maximum power will be delivered to load from a source network when the load resistance is exactly equal to the Thevenin's resistance of the source network. Here maximum power is delivering to what? It is delivering to the load. But when it occurs, when the maximum power delivers to the load, when load resistance must be equal to Thevenin's resistance, then only maximum power will be transferred to the load, otherwise it cannot. Okay, so that is the statement. Now proof. Let us consider Thevenin's equivalent circuit. So Thevenin's equivalent circuit is given here. Okay, so Thevenin equivalent circuit is what? Thevenin equivalent circuit means it contains a voltage source, that is V Thevenin's, and in series that is resistance only, that is Thevenin resistance, and one more is that the load resistance. So Thevenin voltage, Thevenin resistance, load resistance. So Thevenin's and load resistance are always series. Okay. So let us consider Thevenin's equivalent circuit of potential V Thevenin's and resistance R Thevenin's connected to load resistance RL as shown in figure. So just now I have shown you. Now the voltage across the load resistance RL is, so voltage across the load resistance, let it is a VL. So VL is equals to what? This is by using potential divider rules, like current division rule. It is like current division rule. It is a potential division rule. So what is a potential division rule? See here, potential division rule can explain to us voltage across the resistance. Voltage across the resistance, which resistance? Either Thevenin resistance or whatever it is. Okay, voltage across the load is equals to voltage of applied voltage. It is applied voltage into voltage, where we are going to calculate that by total resistances. Okay, total resistance. Here total resistance in the circuit. See here, how many resistances are there? 2 resistances are there. So here we need here what it is, we need here voltage. And if you observe here whatever voltage here, this voltage is see this voltage may appear at this also. Okay, so once again, voltage across the load is equals to voltage of the source into voltage where we are going to calculate. We are calculating, we need it RL by total resistance. How many resistance we have? Only 2 resistance. Those are R Thevenin's and R load. Okay, so that is only it is written here. This is that is the equation 1. Power delivered at the load is RL. Power delivered is, so power formula we know, power is equals to V into I, voltage into current, but it is in terms of V and I. In terms of V and R, it is written as V square by R. Okay, power formula in terms of voltage and resistance is V square by R. So V square. So if you calculate the power at a load, then PL is equals to VL square by RL. Okay, so from the equation VL already we have, take that value and substitute in the place of VL square. So it is substituted and taken from the equation 1. Okay, now write the square individual. So R square V square by RL plus R Thevenin's plus RL whole square written. So here RL square, 1 RL will cancel, 1 RL remains there. Okay, now it is the formula. So now let is equation 2. In this expression, V Thevenins and R Thevenins are constant. To maximize the power, means if you want to increase the power delivered at a load, okay, if you want to deliver the power at a load, maximum power, then what we have to do? We have to differentiate it and make it to 0. Why do we have to make it 0? What I am saying here, power is maximum I am saying at load. So maximum power or minimum power, what values you take, maximum, minimum, or constant. Okay, all these terms in mathematics are always constant. Okay, maximum, either maximum or minimum or constant, all three terms are always constant, they cannot be differentiable. So what I am saying now, I am saying power is maximum, then its part derivation is always 0 with respect to load. Okay, so whatever you take, whatever you differentiate, with the quantity you differentiate the power, so it is always 0. Why? Because power, but I am saying power is maximum. Maximum power means its differentiation is always 0. Maximum means it's a constant. Okay, so let us differentiate the power at load, and that is equation 2 with respect to RL and I equal to 0. Make it to 0, equal to 0. Okay, so to the equation 2, it is I am writing both sides dPL by, see, equation 2 is what? This is the equation 2. So PL is there. So this PL I am differentiating d by dRL, and this side also d by dRL is written to this. Now come into, now differentiation is V Thevenin's is constant. I told you V Thevenin's constant and R Thevenin's also constant, but along with the RL it is there. So it is RL, but we have to differentiate with RL. That means it is a U by V method is there. So what is a U by V method? U by V method is V square into U differentiation, sorry, V, not V square. U by V method is U by V is equals to V U dash minus U V dash. Okay, U V dash minus V U dash minus U V dash. Okay, so that is the formula. So here it is, RL is U, and R Thevenin's plus RL whole square is V. Okay, it is RL, V is what? RL plus R Thevenin's whole square, it is V. So U by V method is once again V U dash minus U V dash by V square. Okay, this is exactly formula. U by V is V U dash minus U V dash by V square. Okay. So here actually we have to write power 4, it is forgotten, so it is a mistake. Why? Because we are by V square we have to do, already square is there, so it becomes 4. Okay, it is also power 4. Okay, so it cannot affect, that is why no changes will occur. But you must write in the examination whole power 4 here. Here also R Thevenin's plus RL power 4. Okay friends. So U by V method, in the U by V method first write U as it is, V as it is, V is written, and RL with respect to RL is 1, yes, minus, next keep it RL as it is, and differentiate V. So V, it is already in the power, it is in the power. So R Thevenin's plus RL whole square is, it becomes 2 into RL plus R Thevenin. So that is why it is 2 into, it is written like this. By power 4 it is has to write, but square is written. Okay, sorry. Now bring next write it as it is. Write a 2 number this side and 1 into this is this one only. So we get it. and bring this power 4 term, it is not square term, power 4 term, and it come this side. When it comes, it multiplies, 0 into something is 0, so that is why it is 0. Now take common factor, which is this common factor take. So common factor is taken, and inside the bracket is this one only, and a common factor also, if it comes this side, it becomes 0, and the remaining terms are Thevenins plus RL minus 2RL. So minus 2RL is there, here RL only, then minus RL becomes, right, minus, what is the minus RL? Why? Because RL minus 2RL is minus RL, so that is why minus RL is written, and Thevenins. So bring this is a minus this term this side, then it is becomes equal. So Thevenins is equals to R load. So what I said, in the above we assumed power is maximum. Generally power is maximum when Thevenin's resistance is equals to load resistance, then only power is maximum. So it means the power delivered at the load will be maximum when the load resistance is exactly equal to the Thevenin's resistance, exactly equal to the Thevenin's resistance here. Okay, so this is the statement of Thevenin's, and we proved it is like this. Okay friends, thank you for watching this video.